Okay, thank you guys for coming. Pretty good turnout for the first review. A little bit about how this works before we start, since this is the first one. So these questions that we're going through they're written by me, so they're not from the actual test bank, but they're designed to be close approximations of the topics that will be covered on the exam and the relative difficulties of the questions. So it's a pretty good model of what you'll see on the exam. But again, remember that the exam draws from a large question bank. Each question has about 15 to 40 different problems it can draw from, so you're not likely to see anything that's identical to this or anything that's identical to each other. So you'll have to be prepared for a lot of different variations on these, but again, the topics and the level of difficulty should be pretty close to what you see here. And then also for this exam review, feel free to interrupt anytime with questions. If you have a question about the specific problem I go over, or just the topic in general that's related to that, please feel free to ask. This is for your benefit, and I'll try to answer those as best I can. All right, so with that, we'll just get right into question number one here. So the first problem in the exam is going to deal with some of those early chemical principles like mass laws, and that's what this problem is about here. So we want to know which mass law is demonstrated by the fact that sodium chloride mined in Goderic, Ontario, the largest salt mine in the world, and sodium chloride mined in Pakistan, the world's second largest salt mine, both consist of 39.3% sodium by mass. So basically your answer choices are, three of the mass laws and then a fourth one, Dalton's law. So in looking at the answer choices here, first we should recognize that Dalton's law is not a mass law. So this is not going to be our answer because it's not even one of the mass laws. There's Dalton's atomic theory, which is related to these laws. It's a theory that explains the mass laws, but Dalton's law itself is something we'll learn about later in the course related to gases. It has nothing to do with the mass things. So then the next three answer choices that we have to consider are the three mass laws that we have. So just like a quick summary of those, so to center your thinking, remember, law of conservation of mass is probably the simplest of the ones, which is that matter is neither created nor destroyed during a chemical reaction. Now, if we look at the situation that's presented in this problem, we're not talking about a chemical reaction. We're talking about just a single substance. Remember, a chemical reaction will be changing one substance into something else. So I think we can eliminate this as being our answer choice. Choice A is not going to be it. For choice B here, just a little note about terminology. It's at some point, I think it's in the new edition of the textbook, they did this because they have to justify selling a new edition every few years. They don't call it the law of definite composition anymore. They call it the law of definite proportion. So I hope that didn't cause any confusion, because I was using definite composition in class, and then the book uses definite proportion, and that's how the exam questions will be modeled based on the terminology in the book. So this should say law of definite proportion, but those mean the same thing. They don't mean anything different from each other. They're just stated in slightly different ways. So don't let that be a source of confusion. Definite proportion, definite composition, they both refer to the situation that all substances have specific mass ratios of elements. And it's most applicable to compounds, which have two or more elements in them, where you can then define a ratio of the two elements in terms of their mass, or mass percent as it's often done. And then finally, choice C here, law of multiple proportions. It's kind of a long and complicated one, but for law of multiple proportions, the dead giveaway is that you need to be talking about two or more substances, and these are substances that are formed from the same elements. So the example I gave in class several times was carbon monoxide, carbon dioxide. Both compounds that have carbon and oxygen in them, just different ratios. So that's what law of definite composition, multiple proportions deals with. It's more complicated than this, but that's sort of the dead giveaway. That's what you're talking about. All right, so again, in this problem, we're not talking about a chemical reaction, so conservation of mass is not relevant. We're only talking about a single compound, sodium chloride in both cases, and we're stating that the composition in terms of its mass percent is the same for both. So all of those should match up pretty well with choice B, which is law of definite proportion, which also is called law of definite composition. All right, so we're talking about a single compound, and we're talking about the composition of that compound. Those situations are covered by that mass law. Okay, any questions on that or the related topics? All right, if not, we'll just keep moving on, because these typically take a while. All right, the next question, which again, you're likely to see something like this on the exam, would be subatomic particles. So moving into the atomic theory of matter and how atoms are constructed from different subatomic particles, the protons, neutrons, and electrons, and specifically looking at a chemical symbol like this, an atomic symbol like this, and being able to determine how many of those subatomic particles they are. So we want to know, in this case, the number of neutrons and the number of electrons that are present in this ion here. So if we write out the chemical symbol, or the atomic symbol, 55Mn3+, is what we're given. So you have to remember what the different numbers in this mean. So this, you'll recall, is the charge. Anything that's on the top right, it'll have a positive or a negative next to it, tells you the charge. This number on the top left is what's called the mass number. All right, and what the mass number tells us is the combined number of protons and neutrons. All right, so it's those two together, so it's not going to tell us anything individually. So we have to be able to find the number of neutrons, we have to know how many protons there are first. In this case, the atomic number, which gives you the number of protons, is not directly provided in the atomic symbol. So what we're going to do to find the number of protons is going to be to go to the periodic table, find the chemical symbol Mn, the atomic symbol Mn, and then figure out its atomic number from the periodic table. So this is the first use of the periodic table that we had. There's going to be a few problems where the periodic table comes into play in this review and in this exam. And so the first one would be, if it ever opens up for me, come on, using the periodic table to figure out the atomic number, the number of protons in the nucleus. All right, so you should become relatively familiar with the periodic table so that you don't have to play a Where's Waldo game every time an element is asked about. So Mn is here in the middle of the transition metals, and the number right above it is 25. So that tells us that the atomic number is 25, which tells us how many protons that atom would have. So from the periodic table, if we know the atomic symbol, the symbol of the element that we're dealing with, we can just find the number that corresponds to that, and that directly gives us the number of protons. Now that answer is not actually part of what we're looking for, but again, we need that to find the number of neutrons. So then to find the number of neutrons, it's just going to be the mass number 55 minus the number of protons, which is 25. So again, this number here, 55, is the sum of the two, so that gives us 30 neutrons. All right, neutrons plus protons equals mass number, so it's just a simple algebra. And then finally, for the number of electrons, if this was a neutral atom with no charge, the number of electrons would be equal to the number of protons. So the number of protons is 25, so if it was just manganese without a charge, it would also be 25 electrons, but we have a +3 charge. So to get a +3 charge, it has to lose 3 electrons, so it's going to have 3 fewer than that, or 22. So anytime we form a positively charged ion, we do that by losing electrons, not by adding protons, but by losing electrons. So again, we're subtracting 3 because of the +3 charge. In this case, we're subtracting from the number of electrons, so that's how we get 22. So 30 neutrons, 22 electrons, that would be choice B in this multiple choice question. All right, most problems would probably have you just do one of those two, but again, it's good to look at both of them. Yeah?
Is a periodic table going to be provided when you take the test?
Yes, so this exact one will be in CASA for you. Okay. I think they just have it hanging up on the little booths where you guys take the exams. Some of you are nodding your heads, so that sounds accurate. I've only gone to CASA like 2 or 3 times. I try to avoid it at all costs, but unfortunately that's not an option for you guys. But anyway, I think they have them posted, and it'll be this exact one. So this one's posted in Blackboard too, so again, it's good to get familiar with what's on there. There's also some constants at the bottom. The only one that's probably useful for this test is these last few here. H, C, and then there's this Rydberg constant, which I don't really use, but could be useful if you know how to use it. But anyway, that's what's going to be given to you, and it'll be provided, and it's exactly that same document. Anything else on this one? All right, on to the next one. All right, so this one deals with the properties of photons. So we have an infrared photon with a frequency of 1234 nanometers. A wavelength of 1234 nanometers. We want to know what are the energy and frequency. So again, this is a 2-part question, really just to give you the different variations that you can have on this type of problem. And we have to know essentially 2 equations that deal with the properties of photons, and then a third one that kind of combines the two. So the first one we talked about is that the product of frequency and wavelength, nu being the frequency, lambda being the wavelength, that product equals c, which is the speed of light. And then the second equation deals with the energy of a photon, which is given by a different constant h times the frequency. And then if we combine these two equations, solve for lambda, and replace nu with that expression, we can also write this as hc over lambda. All right, so these two equations are equivalent, just using nu or lambda in the relationship between them. So those are the two equations you need to know, plus the third one that kind of derives from those two. And we're going to use both of them here. So the first thing we want to know is we can do it in either order, but we want to know the energy and the frequency, so let's just do it in the order they're stated. So the energy in this case, we're given wavelength, so this form of the equation here is going to be a little bit more useful for us. So we'll go hc over lambda. And then we just have to put the constants in. And again, these two constants, h and c, are on the periodic table. But hopefully you've used them enough by now that they look familiar. So 6.626 times 10 to the minus 34 joule seconds for h. 3 times 10 to the 8th meters per second. 2.998 if you're being really exact. And then lambda is given to us as 1234 nanometers. Now what we have to remember with these equations is that wavelengths need to be in meters if we're going to use these equations. Or alternatively, if we're using one of these equations to solve for lambda, the answer will initially be in meters. So we have to do that conversion first. All right, so always write out your units. Again, meters is here in your speed of light, so your wavelength also needs to be in meters for the units to divide out properly. All right, so we've done this a million times also. If you have nanometers and a wavelength, it's going to be 1 meter is 10 to the 9th nanometers, or alternatively 10 to the minus 9 meters is 1 nanometer, mathematically equivalent. So what we get is 1.234 times 10 to the 6th in meters. So that's the number we're going to put down here into the denominator in the correct units. And then what we should end up with is 1.61 times 10 to the minus 19 joules. So A and B have that as the energy, so if we trust ourselves that we did it correctly, the answer is going to be either A or B. And then we have to find the frequency as well. So we'll solve for frequency, which is c over lambda. So same speed of light constant, 3 times 10 to the 8th, same lambda. And that comes out to 2.43 times 10 to the 14th. Probably left off a sig fig, but that's okay. And that matches up with choice A. So that'll be our answer here, where both of those are the correct value. Now be aware that in problems like this, we will sometimes ask you to enter in the number as opposed to just selecting it multiple choice. And there's two formats for entering exponential numbers in Blackboard. So one of them is the sort of 1.23 E4 notation, as we'll sort of give it. So if we were entering this in that format, if they asked you to type the number in, for example, for I don't think we usually do it for negative exponents, but if we did, you would write the energy as 1.61 E minus 19, and then nu would be 2.43 E14. So that's one format that we can ask you to write numbers in Blackboard. Because so when it's times 10 to the whatever, you just put the exponent after the E, kind of like you would in a calculator. And so that'll be specified on the exam. So make sure you're reading closely what answer format we're looking for if you have to type it in. And you don't type in units in Blackboard, it'll tell you what units your answer should be in, and then you just type the number. I'm not opposed to going through and regrading questions manually if I have to, if Blackboard counts it wrong for some stupid reason because of formatting. But at the same time, I don't want to do it 120 times for all you different people. So try to follow the instructions as closely as possible. Also, as we'll see later on in today's class, there are some numerical questions where you'll take the log of your answer and report that instead. So make sure you don't do logs on your calculator. But if this is multiple choice, you would just, of course, select the answer. But if it's numerical, you might have to enter your answer in one of these formats here. For for exponents, and that'll be clearly stated in the problem on the exam. So just make sure you're following it. Okay, any questions on this topic or the problem in specific? Yeah.
Was it positive, not negative, like the 10 to the power of 9?
It's minus 19. So it's minus 34, and 8 is like minus 22, and then you divide by minus.
Like when you convert nanometers to meters?
Oh, well, so there's two ways of writing that conversion factor. So it's either this way. So a nanometer is a lot smaller than a meter. So there's 10 to the 9th nanometers in 1 meter, or you could write it as 10 to the minus 9 meters in 1 nanometer. I just like dealing with positive exponents better than negative, but you can write it either way. It's mathematically the same.
Okay, so let's say like it was 1234 meters. Like you have to convert to nanometers.
Then you have to multiply by 10 to the 9th, which would be a huge number, yes.
And it'll be 10 to the negative 9, right?
If you're converting, if this was in meters, 1234 meters, you would convert that to 1234 times 10 to the positive 9th nanometers, or 1.2 times 10 to the 12th, I guess. So nanometers are smaller than meters, so the number for nanometers is going to be bigger than the corresponding number for meters. So, I mean, think about it this way. You're sitting down, so I can't tell, but you're probably like, here, I'll be generous. You're probably like 6 feet tall, right? If you're 6 feet tall, that means you're 72 inches tall. Inches are smaller than feet, so the number for inches is bigger than the number for feet. Nanometers are smaller than meters, so the number for nanometers is much larger than the corresponding number in meters. So that's kind of how that works with units. Okay, anything else? All right, on to the next one. All right, this one's actually closely related, even though it's worded in a lot different ways. So make sure, again, don't be tripped up by the wording of the exam. Sometimes we give you extraneous information. So here we're talking about the metal hafnium. It's observed that light with wavelength less than 318 nanometers is required to eject an electron from the surface via the photoelectric effect. What is the threshold energy for hafnium in joules? Now, in terms of the concept that's at play here, again, it's dealing with photoelectric effect, which we should know something about. So photoelectric effect is where we have a metal surface, and then we shine light on that metal surface. And in some cases, we will see electrons being ejected from the surface with some kinetic energy that you can measure. Now, again, we're not really dealing with the quantitative aspects of this concept, but we should know the concept at least. And then what's true about photoelectric effect is that the energy of the photon that you're hitting the surface with is given by h times nu, and you will only see electrons coming off if that's bigger than some threshold value, which is called the threshold energy, E0. Okay? But the threshold energy, E0, has a corresponding frequency, has a corresponding wavelength. So in this problem, we're giving you the corresponding wavelength for that threshold energy, 318, and asking you to find what is the energy then that corresponds to that. So even though there's a lot of information in this problem, and even though it relates to photoelectric effect, the math is exactly the same as what we just did. So we're given lambda 0, the threshold wavelength, and the corresponding threshold energy then would just be the same equation, hc divided by lambda. All right, so anytime we're dealing with the energies of photons and relating them to wavelengths, that's really the only equation we have for that. So then, again, going back to the concept of photoelectric effect, if h nu is smaller than the threshold energy, meaning the wavelength is larger than 318 nanometers, then nothing happens, and that's kind of the key idea. But all we have to do here is just use this equation to figure out what's the corresponding threshold energy if the wavelength is given as such. So when we're going to do that, then we just have to plug in the numbers, and we're all good to go. So E0, the threshold energy, is going to be hc over lambda. So same equation as the last one. And then our lambda needs to be in meters for this equation, so we're going to take 318 and either multiply it by 10 to the minus 9 or divide by 10 to the 9th, however you prefer to think about that, and you'll get 3.18 times 10 to the minus 7 meters. So again, much smaller number in meters than in nanometers, because meters is a much larger unit than nanometers. And that's going to be 6.25 times 10 to the minus 19 joules. So that's your threshold energy, and then the threshold frequency would be just that number divided by h. So you can get all those different threshold values, energy, frequency, wavelength, all from these same photon equations. So that matches up with choice D. So again, even though there's a lot of words in this problem, and even though we're talking about photoelectric effect, it's just the same math that we already did. And then it just comes out that way. Okay, so any questions on that? All right, so you might need to know a little bit about the concept of photoelectric effect. As I said, we didn't go into the level of detail of finding out the velocity or kinetic energy of the electron, but you should at least be aware of how this process works. Okay, and then number 5, we have at least one question on the exam that deals with electronic transitions in hydrogen. So when you have the Bohr model for hydrogen, which states that electrons move in circular orbits around the nucleus, and the energy gets higher as you go further and further away, and the electron can move between those energy levels either by absorbing a photon to go to a higher level, or emitting a photon if it starts at a higher level and goes down. So again, that whole idea here, and there will be potentially some numerical problems that deal with that. So here we're looking to calculate the frequency of a photon needed to promote an electron from hydrogen's ground state into the third shell. Report the logarithm of your answer to do decimal places. So this is when we have to, again, enter the log of the answer, which you would sometimes have to do. So anytime we're talking about the Bohr model, which is not explicitly stated here, but you should recognize that, again, is hydrogen, and we're going between two different energy levels and calculating a frequency or an energy or a wavelength associated with that, we should start with this equation here. Now, if some of you are in the other sections, you may have also covered the Rydberg equation. I don't know if any of the instructors do that or not. That sounds familiar to some of you. So I don't cover the Rydberg equation because this delta E equation is sort of general for all different scenarios. So you're going to combine this equation with one of those equations for photons that we've already been talking about already, the relationships between energy, frequency, and wavelength. So you don't need a separate equation. You always start with this one. So this one is not given to you on the periodic table, although I believe in most of the problems where you need this, we'll state the equation in some form, so you won't have to necessarily memorize it, but hopefully you've used it enough that it already is familiar. For hydrogen, we don't have to worry about the atomic number, so we're just going to do the two n values, the final value and the initial value, where those are the two different energy levels that the electron is transitioning between. So now we just have to figure out what those are. So we're going from ground state to third shell, so that means your final n value is going to be 3. That's where the electron is going to. Now again, what does it mean when you're in the ground state? What's the n value for that? 1. So ground state is the lowest energy state of anything. And for hydrogen, that means n equals 1. And so that's going to be our two n values there. Now, if you put them in the wrong order, you're going to just get the wrong sign for delta E, which in some cases is important if we're asking for delta E. If you're trying to find just the frequency or the wavelength like we are here, it's always going to be a positive number, so even if you mess up the signs, you'll end up with the same answer at the end. But it's good to put them in the right order to make sure we're also thinking about it correctly. So again, in this case, we're going from a lower energy state to a higher energy state, 1 to 3, and that should give us then a positive delta E, and that's going to require us to put NF there as 3 and initial there as 1. All right, so when we work that out, we should get 1.94 times 10 to the minus 18 joules. All right, so that's delta E. And then whenever we have a delta E for an electronic transition, then the energy of the photon that's associated with that process, in this case, it's going to be an absorbed photon that causes the electron to be promoted from lower energy to higher energy. The energy of the photon is just equal to the absolute value of that delta E. So it's just that same number. And then once we know the energy of the photon, we can relate it to frequency or wavelength. So those same equations that have already come up a couple times today. So we have the energy of our photon is here, and we're going to just solve for frequency, which is just going to be the energy of the photon divided by h. So here's our delta E, that's equal to the energy of the photon as well, or its absolute value would be, and then we're just going to put that number in and divide by h to get frequency. All right, so that's the energy that we just calculated. H is the constant that's on your periodic table. And what we get, and we should, usually when you're doing numerical problems in the exam, especially if it's one where it asks you to report the number, keep at least one extra significant figure until the end. Don't try to do too much rounding, because occasionally if you round too much, your answer will be outside of the range that Blackboard wants, and then that'll count the question wrong even if you did it right. So don't do too much rounding, and we're not really that picky about significant figures anyway in this course. But then what it asks for is, so that's going to be in hertz, but it wants us to take the log of the answer and report it to 2 decimal places. So again, make sure you know how to do this on your calculator. It's a little bit different for certain calculator models, but the log of that number is going to be 15.47, and it'll specify how many decimal places to report it to, which is usually 2 or 3. Okay, so that's another alternative form. If you're wondering why we do it this way, it's just because many years ago, when a lot of these questions were first created for the test banks, Blackboard was not able to handle exponential answers. So for numerical questions that had exponential answers, the only way for us to deal with it was to have you report the log of the answer, which then Blackboard could easily accept. Now, we have some questions that are in different formats because Blackboard can handle exponential formats now with no problem, but you might see some of these relics as well. All right, so any questions on that? Either the concept or the mathematical operations that I did. All right, yeah, sorry, go ahead.
So if it was going from a high to low, would it be a negative and then the number would be negative?
The delta E would be negative. So yeah, the question was, I should repeat the question because I'm not sure if people online can hear it. The question was, if it's going from a higher n value to a lower n value, would it be negative and would it be emitted? So yes, the delta E would be negative in that case, and you would be emitting a photon. The frequency or wavelength of the emitted photon is still a positive number. You can't have a negative frequency or a negative wavelength. So that's why there's this absolute value term here. So the energy of the photon would be emitted instead of absorbed, but it would still be a positive number for any wavelength or frequency you calculate from that. Yes. Anything else? Okay. Let's make sure we keep going. All right. This question is about electron configurations. So we want to know, what is the ground state electron configuration for manganese? All right, so make sure you know the names and the symbols for the first 36 elements. There are questions where that's going to be required information. It's on the syllabus, so it shouldn't be a surprise at this point. So for all 36 elements, the first 36, I guess we have a periodic table in this room, so you can take a quick glance if you don't have one convenient to you. But you'll need to make sure you can match up the name and the symbol, because the periodic table that you have only has the symbols on it. So here we're looking for manganese. So there's some names that are similar, but manganese, the symbol for that is Mn. Okay. So we got to find that in the periodic table. So again, the way that I like to approach electron configurations is to use the periodic table to tell us which order we're going to fill the subshells. Now, typically, in most cases, especially for the heavier elements near the middle or bottom of the periodic table, the core electrons are going to be written in terms of the nearest noble gas to that element, the one that comes before it. So if we're here at Mn, which is number 25, the noble gas that comes before it is argon Ar. So we can abbreviate those 18 core electrons with just Ar in brackets, telling us that all of those subshells, 1s2, 2s2, 2p6, 3s2, 3p6, all those are filled with those first 18 electrons, and then we'll indicate the valence electrons explicitly that come after that. So for Mn, we're here. So after this, we're going to the fourth row of the periodic table. So we start with 4s in this first two columns. So that's going to be 4s1, 4s2. After 4s comes this middle part, which is 3d and minus 1d block. So it's going to be 3d, 1, 2, 3, 4, 5. So that means we need 5 electrons to get to Mn. And then, so that's the correct configuration for Mn. So we start with the argon core. After that was 4s2. And then after 4s, remember, was 3d. All right, because when we're in the fourth row of the periodic table, we start with the 4s block, but then after 4s is the n-1, which is 3d, the first of the d sections. So the one that matches up there is A. So this one has 4p being filled before 3d, but 3d comes before 4p on the periodic table. This one has the wrong n value for the d's. It should be 3d, not 4d. This one has the wrong n value for the 4s's. It should be 4s before 3d. So all these have the correct number of electrons, but only choice A has them in the correct subshells. So when you're doing problems like this, where you're given an element and asked to find the electron configuration, probably the first thing you should do, and you can eliminate a lot of answers this way, and if you're lucky, you can just pick the right one, is just figure out how many total electrons each given configuration has, because it has to have the right number of electrons. If the number of electrons are wrong, then it doesn't matter what subshells they're in, it can't be the right answer. All of these would have 25 because it's 18 for argon, and there's 7 more listed. So for these ones, you can't really use that to help you. You have to go through all of them to make sure you find the one that's actually correct. But in other problems you might have on the exam, some of the configurations you're given might have the wrong number of electrons. They might have 26 or 35 or 32. Manganese is atomic number 25, so whatever answer you pick should have 25 electrons in it. And so you can ignore all the rest. But for this one, they all have 25, so you have to go through and figure out which one is written in the correct way. Okay, so any questions on that problem or electron configurations in general? Okay, on to the next one. All right, the next question deals with relationships involving the different quantum numbers. So we want to know how many orbitals are in the sublevel where n equals 5 and L equals 4. So a little bit about the terminology before I go into answering this specific question. So if we're talking about a shell, that's going to be defined by an n value, and the number of orbitals that are going to be in that is given by n squared. So if we're just given the n value, or we're told it's the first shell, second shell, third shell, fourth shell, whatever, if it's a shell number that we're given, you just use n squared. If it's a subshell or a sublevel, as it's called here, for that you're going to be given an n and an L value, or it could just be given as the L value for a more generic sublevel that's not specified. But in either case, if you have the L value given as part of that, when you're talking about a subshell, the number of orbitals is determined by the L value, and it's given as 2L plus 1. All right, so those are the two relationships for how many orbitals are in a shell and then how many orbitals are in a subshell or a sublevel. In this case, we're talking about a sublevel, and we're given an n and an L value. So in this case, we don't even need to worry about the n value. We're just going to use the value of L. So for this particular problem, the number of orbitals will be given by 2L plus 1, which L in this case is 4, so that comes out to 9. So there'd be 9 orbitals in this sublevel here. And again, it only depends on the value of L. So whether this was n equals 5, L equals 4, n equals 6, L equals 4, n equals 7, L equals 4. If L equals 4, that's how many orbitals are going to be in that sublevel for any of them, regardless of what the value of n is. So you didn't even need the value of n here. Okay, so that's how we get number of orbitals. A very related type of question would be how many electrons maximum can go into a shell or a subshell. And for that, you just have to remember these relationships here, and then, of course, that for each orbital, you can have a maximum of 2 electrons. So in a shell, the maximum number of electrons, again, this is maximum number, not necessarily how many there will be, is just 2 times n squared. N squared is the number of orbitals. Double that to figure out how many electrons could go into those orbitals. And then for a subshell, the number of electrons is just 2 times 2L plus 1. 2L plus 1 is the number of orbitals. Double that is the number of electrons that can go into those orbitals. So those are going to be related here, where though we're just looking for a number of orbitals. So we wouldn't want to use the 2L, we wouldn't want to double the number, we would just want to stick with 2L plus 1. All right, questions on that? I think there's at least one more. Yeah, this one also deals with shells and subshells. Okay, so again, a two-part answer here. What is the maximum number of electrons allowed in the n equals 5 shell, and how many of these can reside in the 5F subshell? All right, so again, we'll start with the first one, which is in an n equals 5 shell. As we just finished saying, the number of electrons that you can have in any given shell is equal to 2n squared. All right, where it's, again, n squared is the number of orbitals, 2 times that is the maximum number of electrons. So for n equals 5, it's just going to be 2 times 5 squared, which is 50. So that means in the entire n equals 5 shell, we can put at most 50 electrons. So that eliminates some of the answer choices already. But we have to figure out which is correct for the second part, which is how many of those electrons can go into the 5f subshell. All right, so of these 50 electrons, they're going to be distributed into 5s, 5p, 5d, 5s, 5p, 5d, 5f, and there's also a 5g as well, which is not one we need to normally consider, but would be possible subshell for n equals 5. So then for the subshell, the number of electrons, as we said, is 2 times 2l plus 1. Now here we're not given a numerical value of L, but remember that anytime we label a subshell with a number and a letter, the number is the N value, the letter corresponds to what the L value is. So the different letters that we have would be, so the different values of L we can have are 0, 1, 2, 3, 4, and so on. And the L values that correspond to those are S, P, D, F, and then after that is alphabetical. So G, H, and you're probably not going to go any higher than that anyway. Okay, but these are the ones that we normally see because these are the ones that occur in the periodic table. All right, so if we have an 5F subshell, that means L equals 3, so that's going to be the L value we use in this relationship. So 2 times 3 plus 1, which is 2 times 7, or 14. All right. So the correct answer for this would be C. Now the other way to approach this, which works if you have an SPD or an F subshell that you're talking about, is to use the periodic table. So the 5F subshell is shown here on the periodic table. It's this last row here is 5F. And if we count how many elements are in there, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 elements in the 5F block, which means there's a maximum of 14 electrons that can go into the 5F subshell. So that works if you're talking about S, P, D, or F, because all those are different subshells are on the periodic table. But if you're going higher than that, G or H or whatever, you need to use the equation that I gave you, 2L plus 1, and then double that for the maximum number of electrons. Okay? So there are a couple ways of handling that one, but these relationships are helpful at times, these 2L plus 1 and n squared relationships. So just know when to use them and you know what they mean, and you should be good to go. Any questions on that? Yeah.
What was not the category, but the type of question this is called?
This type of question would be quantum numbers, I suppose. So there's, I mean, I did this on purpose. It looks like there's probably, based on how I have it on the review, there's going to be up to 3 problems on the exam that deal with quantum numbers. So, the previous one, this one, and then I think the next one also. So, yeah, that topic seems to be favored by whoever put the exam together, so which wasn't me. So make sure you're familiar with those because they'll come up on the exam for sure. Yep.
What principle says that there's only like 2 electrons per shell?
So the principle that, it's not 2 electrons per shell, remember, it's 2 electrons per orbital. It's 2n squared per shell. The principle that dictates that there can only be 2 electrons per orbital is called the Pauli exclusion principle. So Pauli exclusion says that you can have, so no 2 electrons in an atom can have the same set of quantum numbers. So when you define an individual orbital, an orbital is defined by 3 quantum numbers, n and L, which we've already seen, and then another one, m sub L, that specifies the individual orbital. So for example, we saw that there's 7 orbitals in the L equals 3 subshell, so each of those is going to have a different m sub L value to distinguish those 7 from each other. So those 3 together define one orbital, but then the electron itself that goes into that orbital can have a spin value, electron spin value, m sub s, that's either plus 1/2 or minus 1/2. And since no 2 electrons can have the same 4 quantum numbers, if you're putting 2 electrons into the same orbital, one has to be spin up, one has to be spin down, and you can't put a third one in there because there's no third possibility for the m sub s value. So that comes from the Pauli exclusion principle is what it's most related to. But it doesn't matter what type of orbital it is. It doesn't matter what the n, L, and m sub L values are. Only 2 electrons can go into any single orbital. All right, other questions? Yeah.
Why would you use 3 for L again?
So the reason we use 3 for L is this is a 5F subshell. So whenever the subshell is designated as a number and a letter together, the letter tells you what the L value is. It corresponds to L equals 0, 1, 2, 3, and so on. And the letters are S, P, D, F, and then alphabetical after that. Okay.
And where do you get the 2n squared from? Where do you get the 2 from?
So the 2 is because, as we talked about in the last problem, the number of orbitals in a shell is n squared. And then, as was just asked earlier, there can be up to 2 electrons per orbital. So there's n squared orbitals, but then the number of electrons you can put into those is 2 times n squared. So that's where the 2 is used in both of these, because here we're looking for the maximum number of electrons, not the number of orbitals. So they're related to each other, but it depends on whether the question is asking for the number of orbitals or the number of electrons, whether you have to use the factor of 2 or not. Okay. All right, this next one also deals with quantum numbers. So as we said, and was just addressed in the previous question, each individual orbital is defined by 3 quantum numbers, n, l, and m sub l. And in this problem, we want to know what is an allowed set for a 4D orbital. All right, so remember the n values that are allowed are positive integers, 1, 2, 3, 4, and so on. And then the L values that are allowed start at 0, and the maximum value is going to be n minus 1. So depending on what your n value is, that's going to dictate which values of L you can have with that. And then the one that we haven't talked about yet is m sub L. So the allowed m sub L values are going to be minus L, including 0, all the way to plus L. And again, each individual orbital has a unique m sub L value to distinguish those orbitals from one another. So here we're looking for a 4D orbital. And from the relationships that we just talked about, if we're talking about a 4D orbital, we're talking about an orbital where L equals 2. Okay? So that again, when you have the number and the letter together, the letter tells you your L value. And we recognize from the relationships given in the previous problem that there should be 5 of those 4D orbitals. 2L plus 1 is 5 for L equals 2. So there's 5 4D orbitals, which all have different m sub L values. So for L equals 2, then the allowed m sub L values are going to start at minus L, so minus 2, including, and then we're going to space them in integers of 1 up until plus L. So these are the 5 allowed m sub L values, and that's why you would have then 5 4D orbitals. 2L plus 1 is 5. Okay, so those are the possible m sub L values, and we have to see which of these answer choices has everything in the right order. So 4D tells us that n equals 4, and as we said, L equals 2. So the first two need to be 4 and 2. So we can get rid of C because that's the wrong L value. We can get rid of E because that's the wrong L value. Again, for a D orbital, L has to be equal to 2. And then for A, B, and D, we have the first 2 quantum numbers correct, 4 and 2 for 4D. Now I have to figure out which of those has an allowed value for m sub L. So as we said, m sub L can be anything between minus 2 and plus 2. So 3 is too big, so that one can't be right. It's never going to be a half integer value, so that one can't be right. So the only answer that has all 3 quantum numbers correct is choice A. 4, n equals 4. 2 corresponds to a d orbital for the L value, and then minus 2 is one of the 5 allowed values for m sub L. So any of these 5 would have been fine, but in this case it's given as minus 2. All right, so it's also helpful to know the relationships between the different quantum numbers you have. So there's kind of a hierarchy between them where the n value is any positive integer. Once you define the n value, there's different possible L values, and then m sub L follows from whatever your value of L is for the subshell. Okay? Any questions on that? All right, I think that's our last one on quantum numbers. So any last questions on quantum numbers, get them out now. All right, the next one deals kind of with quantum numbers, more about electron configurations. All right, so this one is that we want to know which of the following orbital diagrams reflects an atom in the ground state. So remember, ground state means the lowest energy configuration for an atom. For hydrogen, it means n equals 1, but for multi-electron atoms, there's going to be the electrons distributed into different subshells. And if we follow the ordering of the periodic table, that's going to give us the correct order of the subshell. So there's essentially 3 rules we have to follow, or make sure are being followed in these examples, to state that the electron configuration is correct for the ground state of that atom. So the first one is called the Aufbau principle. And this is the principle that states that we're going to fill the subshells from lowest to highest energy. So again, when we follow the order of the subshells that's given from the arrangement of the periodic table, we are following the Aufbau principle. We're going from the lowest energy subshells, filling those first, on to higher and higher energy subshells as we add more electrons. That's what the Aufbau principle states. So for the ground state, that needs to be followed. The other thing that needs to be followed is called Hund's rule, which is stated very briefly. We want to maximize the number of unpaired electrons. So this comes into play if we have degenerate subshells that have more than one identical orbital at identical energy, and we want to make sure that we're filling those orbitals one at a time, all with the same spin before we pair up two electrons into the same orbital. So that's Hund's rule. And then the last one is, as we already mentioned a little bit today, you have to follow the Pauli exclusion principle. So that means no two electrons can have the same quantum numbers. So when it comes to electron configurations, the consequences of Pauli exclusion, as we've already mostly said, are no more than 2 electrons per orbital. And if you have 2 electrons in the same orbital, one has to be spin up, one has to be spin down. So that's where Pauli exclusion principle comes in. So basically, we're going to try to find the electron configuration here that obeys all of these 3 rules. All right, so if we go to the first one here, A, it looks like Aufbau principle is fine because we filled the 1s, then we filled the 2s, and then our last 2 electrons go into 2p. But what we notice is that in the 2p orbitals, one is spin up, one is spin down. Hund's rule states that we should maximize unpaired electrons, which means if you have 2 degenerate electrons in a degenerate subshell, they both need to have the same spin. It doesn't have to both be up necessarily, but if one's up, the other one has to be up, or if one's down, the other one has to be down. So this one, because of this spin down electron here, this one violates Hund's rule. So that one's going to be out. In choice B here, what we'll notice is that our 2s orbital, our 2s subshell, which has just a single orbital in it, is only partially filled, but we have electrons also in 2p. So basically this one does not follow the Aufbau principle because we're not filling up the lower energy subshell before we start putting electrons into the higher energy subshell. So this one violates the Aufbau principle, so that's not going to be our correct choice. Because again, we didn't fill up 2s before we started putting electrons in 2p. If we look at choice C here, this one looks good to me because we follow the Aufbau principle. We fill the 1s, we fill the 2s, and then our last 2 electrons go in 2p. In the degenerate 2p subshell, both electrons are in different orbitals, and both electrons have the same spin. Doesn't matter which 2 orbitals they're in, they just have to be in 2 different orbitals, and they both have to be spin up or both have to be spin down. So this one follows all of the rules. And so this would be the correct answer choice. And then quickly for choice D, to verify that this one is not correct, we follow the Aufbau principle. 1s is filled, 2s is filled, and then 2p. But we see that for 2p, we put the 2 electrons into the same orbital with opposite spins. So again, this is going to be another violation of Hund's rule. For Hund's rule, if we have 2 electrons in a set of 2p orbitals, they need to be in 2 different orbitals and they need to have the same spin, both up or both down. Yes?
Is there one element that makes an exception that looks like B? As in like one electron from...
So there's 2 elements that you should know of that violate the Aufbau principle. So those are going to be chromium and copper. So chromium, the correct configuration is 4s1 3d5. So it's never going to be violated for 2s and 2p, but for 4s and 3d, which are really close to each other, you can at times violate the Aufbau principle. So you get for chromium, instead of 4s2 3d4, you only half fill the 4s and put one of the electrons up to 3d. And then for copper, similar story. It's going to be 4s1 3d10. So you'll half fill the 4s and then fill the 3d. So there are 2 that violate the Aufbau principle that you need to be familiar with. But never happens in the 2s and 2p subshells, and in a problem like this, you want to make sure that you just choose the one that follows those 3 rules. Yes?
So why did you say C follows all the rules even though it didn't feel like...
The second before the third?
All right, so when you're filling up, so the question was, why does C follow all the rules, even though we didn't fill the second orbital here? So in Hund's rule, you have, in this case, all three 2p orbitals are at the same energy. And by convention, we fill them left to right, but you don't have to. So as long as you fill the electrons in two different orbitals, and as long as they have the same spin, those are all equivalent. So in reality, there's at least 3 different ways, or actually 6 different ways of writing this configuration. So you can write it, with both electrons spin up in any combination of 2 orbitals, or both electrons spin down in any combination of 2 different orbitals. All of those would technically be correct. So there's a lot of different possibilities that would work. And this is one of those 6 possibilities. So it's more convenient and more common to just fill in one orbital at a time left to right, but it doesn't have to be done that way. And if you do it where you skip one of the orbitals, that still represents a valid ground state because those orbitals are all at the same energy. So it doesn't matter which one you fill first. Any other questions? All right, we're halfway there. Reminds me of a Bon Jovi song. Okay. All right, so this question deals also with the periodic table and how we can classify elements and then predict the charges of the ions they form, again, using the periodic table. So we want to know which of the following shows the correct classification and the expected monoatomic charge for the given element. So monoatomic ion charge means if that atom loses or gains electrons to form an ion, what's the charge that ion going to be? Is going to be positive or negative, and what's the magnitude of that going to be? You can use the periodic table to predict that, especially for the main group elements. So let's go through the 3 answer choices here. Okay, so what we have for these is, I'll just wing it. All right, so for number 1, we have potassium. So again, we need to know the symbol that goes with the name. So potassium is symbol K on the periodic table. Number 2 is aluminum, which is Al. And number 3 is selenium, which is Se. So we're going to go through all of these and we're going to figure out what are they classified as, and then also what's going to be their charge if they form a cation or an anion in an ionic compound. Okay, so let's go through potassium first. All right, so K is here in the first column of the periodic table. So anything on the left side is a metal, so K would be a metal. And the ones that are in the first 2 columns and then the few metals that we have over here in the P block are called main group metals. And then, of course, there's all these subcategories too. So there's going to be alkali metals, alkaline earth metals. So there's a few different ways of classifying things, but this would be a main group metal first and foremost. And then if we predict the charge that's formed by potassium, remember that anything on the left side of the periodic table is going to lose electrons until they achieve the nearest noble gas configuration. So potassium is here, number 19. If it loses 1 electron, it will achieve the configuration of argon, which is number 18, one before it. So we predict that potassium, or any of the metals in this first column of the periodic table, would all form +1 ions. So if we go back to the answer choices, so what potassium should be is it's a main group metal, or more specifically an alkali metal. But we would predict that the charge that it forms is +1 because it's in that first column of the main group metals. So here the charge is given as +2, so that part is incorrect, so we're not going to choose choice 1. And then if we go to aluminum Al, so Al is in a little bit of a weird spot in the periodic table. So it's right here. If you recall, the periodic table has this imaginary staircase that separates metals from nonmetals. Aluminum is right below the staircase. So it actually is classified as a metal. It's on the left side of the staircase, so it's classified as a metal. And I think you guys are familiar with aluminum from aluminum foil and probably other things. It's shiny, it's silver. I mean, that's classic metal, right? So this is definitely a metal, even though it's kind of close to the non-metal section of the periodic table. So it is a main group metal. And then in terms of predicting the charge of the ion that forms, I don't think this is one that I went through in class, but we should be familiar with it. So the electron configuration of aluminum, the valence configuration, is 3s2, 3p1. So it has the 2 3s electrons, then it has 1 3p electron to finish up this configuration. So it has a total of 3 valence electrons, 2 from the 3s, 1 from the 3p. And it will lose all 3 of those valence electrons to get to the neon configuration. So even though it's, again, not in the most obvious place in the periodic table, aluminum has 3 valence electrons, and it will lose all 3 of those to form a stable +3 cation that has the neon configuration. So that's one you need to be familiar with that we probably hadn't talked about before. All All right, so for aluminum, it's also a main group metal because it's in the P block of the periodic table, so that classifies it as main group. S and P block are called main group. And then it's going to be a +3 cation when it forms ionic compounds. It loses all 3 of its valence electrons to get to a +3. So this one is correct. And then if we go to selenium, which is Se, selenium is over here. It's clearly to the right of the imaginary staircase, so it's a non-metal. So it's a non-metal element, and then it's going to be in the non-metal side, so we expect it to form an anion. So when it forms an anion, it's going to gain the number of electrons that it needs to get to the nearest noble gas. And so this time it's going to gain 1, 2 electrons. So this whole column here, oxygen, sulfur, selenium, if it forms an anion, we expect it to be a -2 anion because they need 2 more electrons to get to their nearest noble gas. So selenium, the correct classification is non-metal. And we expect the anion charge to be -2. That all matches up. So both of those are correct. 2 and 3 are both correct. So choice E would be what we would choose here. All right, so again, we can use the periodic table to classify elements and also to predict some things about the charges of ions that form, and both of those concepts were covered here. Yeah. Yes. Yeah, so the question is, are nonmetals expected to gain electrons? And that is correct, because when you're to the right of the staircase, over here on the right side, it's easier for them to gain electrons to get to a noble gas than to lose, 5 or 6 electrons. So it's more, and they're also more electronegative, more, they have higher electron affinities, so they'd rather gain electrons than lose electrons, and so they do that to get to the nearest noble gas, and they would form anions whenever they're involved in ionic compounds. All right, any other questions? Yep.
I read a rule and I just want to make sure that it's right. For questions like these, to find the charge, for a metal, it would be the same as the group number, and for a non-metal, it would be the same as the group number -8. Is that true?
Yeah, that should work.
Okay.
Yeah, if you're talking about the main group, which is the only ones we'll deal with on the exam. So for these main group elements, they're numbered with the A group numbers, so 1A, 2A, 3A, 4A, 5A, 6A, 7A. So for the main group metals that are in the first 2 columns, the group number tells you the positive charge that they would expect it to have, so +1, +2, and then, that group number -8 would give you the negative charge that you'd expect for the nonmetals. Again, the only one to be careful with is aluminum, because it is in the P block, but it's a metal, so it would form +3.
Okay.
So you don't want to do 3 -8 -5. It doesn't form a -5 anion, it forms a +3. So be a little bit careful with that one, but the rest of them that are common, oxygen, fluorine, all those, that would work fine for those. Yeah. Okay, other questions? All right, on to number 12. So the next couple of questions deal with periodic trends, which is yet another thing we can do with the periodic table, using it to predict the relative ordering of different atomic properties, where radius, ionization energy, electron affinity are the big 3 that came up in chapter 2. And then chapter 3 also dealt with electronegativity, which is a property of atoms that are covalently bonded to each other. So there's a few different properties we're going to be aware of. So this one deals with all 3 of those first ones: atomic radius, ionization energy, and electron affinity. So we're comparing here oxygen and nitrogen and wanting to know, of those 3 properties, how do they compare to one another. So we're going to do radius for nitrogen and oxygen. We're going to do ionization energy for nitrogen and oxygen, and we're going to do electron affinity for nitrogen and oxygen. So the radius trend is fairly straightforward. You have to remember what it is, but there's not really any exceptions of it that you have to worry about. So the atomic radius is going to increase as you move down the column. So if you're going from top to bottom, you're going to have the radius is going to get bigger and bigger. And that's because, remember, that the row of the periodic table that you're in, 1, 2, 3, 4, 5, 6, and so on, tells you which shell the valence electrons are in. And so as those electrons go to higher and higher shell numbers, they get further and further away from the nucleus. That makes the atom bigger. So moving top to bottom is pretty obvious why they get bigger. Now the one that's less obvious is which direction do they get bigger, moving left to right or right to left. They will actually get bigger as you move right to left. And that's because as you're in the same row of the periodic table, you're putting electrons into the same shell, which are roughly the same distance away. but as you go further and further to the right, you're adding more protons to the nucleus, so that pulls those electrons a little bit closer and makes the atom smaller. So as you go left to right, the radius actually decreases. It would increase going right to left. So you have to remember that that's the trend for radius. So for nitrogen and oxygen, they're right next to each other in the same row. So we would expect oxygen to be smaller than nitrogen. It's to the right of nitrogen. It has more protons in the nucleus, and the net effect is that it pulls its valence electrons a little bit closer, and that would cause it to be smaller. As I said, there's not really any exceptions to radius that you need to worry about. So comparing nitrogen and oxygen in terms of their radius, we expect nitrogen to be bigger because it's to the left of oxygen. They're both right next to each other, so that's an easy comparison. In terms of ionization energy and electron affinity, here's where we have to worry about a couple of exceptions. All right. So for ionization energy, as we go through the different group numbers, this is not nearly big enough. Let's just do it for the P blocks. Let's just do 3, 4, 5, 6, 7. All right, so as we go through the different groups on the periodic table, the different columns, it's going to be relatively low for group 3. It's going to increase for group 4, and then group 5 is going to be abnormally high, and then it'll come down again before group 6. And then it's going to shoot way up for 8 if you care about that one, but that's like super high. All right. But anyway, the point is that when you get to the P block of the periodic table, there's a little bit of a peak in the ionization trend as you get to group 5. Group 5 is higher than both of its nearest neighbors, 4, and 6. Okay? So if we look at the periodic table here, nitrogen is in group 5, so we expect that its ionization energy will be bigger than both of the elements on either side of it. So the ionization energy generally increases left to right, but as I said, there's an exception here at group 5 as well as one at group 2. Where in group 5 and group 2, they're going to have higher ionization energies than both of the elements that come immediately next to them on either side. So nitrogen is higher than carbon, and it's also higher than oxygen. As I said, there's a little bit of a peak there. So when we're comparing ionization energy, even though oxygen is to the right of nitrogen, its ionization energy is smaller. That's one of the exceptions you need to know to the ionization trend. Okay, so for nitrogen and oxygen, nitrogen has a larger ionization energy than oxygen. And then if we do electron affinity, we have the same breaks in the trend, but in the opposite direction. So electron affinity is sort of a measure of how much an atom wants to gain another electron, how likely it is to form an anion, if you want to think about it that way. And again, when we get to this fifth group here, group 5 on the periodic table, if we're looking through the P block, the electron affinity generally increases left to right. That means it gets more negative or it's more favorable to add electrons. But this time what we have is we have a dip at group 5. And then we don't really have to think about the electron affinity for group 8. They have no electron affinities. That one craters again, but we won't even ask about that. But again, right here at group 5, there's a dip in the trend, and it's really for the same reason. Basically, when you have in group 5, remember that your valence configuration is 2p3. So putting one electron into each p orbitals is better than trying to force a second electron into one of those orbitals. So you're increasing electron-electron repulsions a lot because you're adding a second electron to the same orbital. And so what that means is that when you're at the 2p3 configuration in group 5, like nitrogen, you don't want to gain more electrons, so you have a low electron affinity, and you don't want to lose electrons, so you have a high ionization energy. So in both places. So when we're comparing nitrogen to oxygen for electron affinity, oxygen would have a higher electron affinity than nitrogen, which it's to the right, so it follows the basic trend, but again, there's a dip here at group 5 that you should be aware of. So that one doesn't really violate the trend. The electron affinity generally does increase left to right, but again, there's a dip there at nitrogen that you need to be familiar with in general. Okay, so those are the three comparisons. So the first one, the atomic radius of oxygen is larger than nitrogen. That one's wrong. The ionization energy of oxygen is larger than nitrogen. That one's wrong. The electron affinity of oxygen is larger than nitrogen. That one is correct. So choice C would be the right answer here. A and B have the trends reversed for those two elements. All right, so any questions on periodic trends?
Ionization and electron negativity is not the same, right?
Ionization energy and what?
And electron negativity.
They're not the same, but they have the same trend. So they both, so all three of them, except for radius, generally increase as you go up and to the right. So that would be true for ionization energy, electron affinity, and electronegativity, which comes a little bit later in the discussion. So that's going to be true for all of them. But again, there's some exceptions or some blips in the trend when you're talking about ionization energy and electron affinity that you need to be familiar with. For radius and electronegativity, the trends are very smooth, so it's not as difficult. Yes?
So I know this isn't about boiling and melting point, but is it going like this way, the trend?
So there's a question about boiling point and melting point, which at this point you shouldn't worry about. So I think there might have been a homework question on that, but we should have scrubbed it. It shouldn't have been on there. I check the exam questions very closely. I don't check the homework questions very closely, or at all, I guess, if I'm being honest. So there's probably some homework questions that are maybe not, a little bit out of bounds. It's okay, it doesn't hurt you. But then, yeah, so for melting point, we'll come back to that later on in the course and how that relates to, mainly to the atomic radius. So it kind of follows, we're going to mainly do it for the metals, where we're talking about, elements that exist as solids and would have a well-defined melting point. And for the metals, the melting point is sort of inversely related to the atomic radius. So the bigger the radius, the lower the melting point in general. But there's more to it than that. But we're not covering that until the very end, chapter 9. So we're ways away from that now. Okay, anything else? All right, question 13 also deals with ionization energy. So we have nitrogen, oxygen, carbon, phosphorus, germanium, and we want to find the one that has the largest. All right, so again, nitrogen, oxygen, and carbon are all in a row. And as we just finished saying, for those elements which are in groups 4, 5, and 6, we have a little bit of a peak in the ionization energy trend, where the ionization energy of nitrogen is higher than both of its neighbors. That's going to be true for all those group 5 elements. So we just cover that in the last problem, and it comes up here as well, where you have a peak in ionization energy for nitrogen, carbon, and oxygen. So for the largest one, we can get rid of carbon and oxygen because nitrogen is higher than both of those. But now we need to compare nitrogen to the other two, which are phosphorus and germanium. Now if we look at the periodic table, again, nitrogen is here in the second row, phosphorus is right below it. So in general, the ionization energy is going to decrease as we go down. It's the opposite of radius. So we would expect phosphorus to have a smaller ionization energy than nitrogen. It still would have sort of an abnormally high one because it's in group 5, but it's below nitrogen, so in an absolute sense, it should be less than nitrogen. And then similarly, germanium is even lower in the periodic table and it's in group 4, not group 5. So we expect the ionization energy to continue to go down as we go further down and to the left. Okay, so again, the general trend is ionization energy increases left to right and bottom to top. So in this direction, as I'm sort of sketching out there. And then nitrogen would be the one that's the highest of these. So because again, it's in group 5, so it's going to be higher than both its nearest neighbors, carbon and nitrogen. All right, so that's going to be a really similar argument to the last one, where we would select nitrogen as being the highest of these three. Again, it's higher than phosphorus because it's above it in the periodic table, higher than germanium because it's both above and to the right of it. Yes?
Nitrogen wasn't one of the choices, which one would have the highest ionization?
If what was one of the choices?
Nitrogen wasn't.
If nitrogen wasn't the choice, then it would be oxygen. So yeah, you don't see so yeah, carbon versus oxygen. Oxygen is clearly higher. And then, I mean, it might be a little bit hard to compare phosphorus and oxygen, to be honest, so we probably wouldn't have you do that, because when you go to phosphorus and oxygen, it's sort of two competing trends. Oxygen is above it, but then because phosphorus is group 5, it's abnormally high. I believe oxygen is higher than phosphorus, but it's not the one that's easiest to predict, so we wouldn't have. So we typically avoid comparisons that are ambiguous like that. So don't worry about us trying to trick you. We're not that mean. I wouldn't say we're nice either, but we're not that mean. All right. Any other questions? Yeah.
Why is nitrogen bigger than carbon?
Well, nitrogen is bigger than carbon. It's generally it increases left to right. But then nitrogen is sort of abnormally high. So if you draw sort of like a linear trend through all the different ionization energies, nitrogen and the group 2 element that's in the same row as it, which would be beryllium, that would be abnormally high as well. So it's just a little bit off the trend, and it's always going to be higher than group 4 and is higher than group 6, which is sort of the exception that you wouldn't predict necessarily. All right, anything else? Okay. Onward and upward. All right, so now we're sort of transitioning into chapter 3 material, sort of. So we want to know which of the bonds has the smallest ionic character among the following. All right, so we're talking about ionic character. That's just another way of saying polarity. So there's, two different related terminologies that we use, but they mean the same thing. So smallest ionic character is another way of saying least polar. So if we had asked the question, which is the least polar, it's exactly the same question. It's just two different ways of saying it. Okay, so ionic character. So remember, the concept of polarity is that, and I've been explaining this to a couple students that came to my office recently, so I think it is one that's worth going over for everyone. Remember, polarity is sort of a continuum between two extremes. So if we have the same element bonded to itself, where the electronegativity values of the two elements are identical, this would be a nonpolar covalent bond, or what we sometimes call a perfect covalent bond. And that means that the electrons are shared exactly equally. There's perfect, equal sharing of the electrons, 50-50. And then the other extreme would be ionic bonds. So if we have a metal and a nonmetal, as you should be also familiar with, those tend to form ionic bonds, where the nonmetal completely removes the electron from the metal, and you get a cation and an anion where the electrons are no longer shared. But there's an electrostatic force holding them together. So that's sort of the other extreme is ionic. And then polar covalent bonds are anything in between. So like, for example, HCl. This would be a polar covalent bond. They're both nonmetals, but they have different electronegativity values. Chlorine has higher electronegativity than hydrogen. So you'd expect a little bit of a partial negative charge on chlorine, a little bit of partial positive charge on hydrogen. That means that the electrons are being unequally shared by the two elements. They're covalent, but they're not sharing them equally. So this would be what's called a polar covalent bond. So basically, percent ionic character is another way of saying how polar is the bond. A totally covalent bond has 0 ionic character. A perfectly ionic bond is 100% ionic character, and then there's everything in between for the polar covalent bonds. But we're not going to really quantify that. We're just going to sort of rank them relative to each other. And what determines the ionic character, if you have a higher ionic character or more polarity, that means you have a larger difference in electronegativity. So each atom is going to have an electronegativity value, and the bigger the difference, the more ionic character you have. So for ionic bonds, what we classify typically as ionic, you have a really big difference in electronegativity, a metal and a nonmetal. Metals have very low electronegativity, nonmetals have very high, and when the difference between the two is big, the bonding looks more ionic. If you have no difference, that's going to be a perfect covalent. If you have a sort of intermediate difference in electronegativity values, that's where you get polar covalent. Sorry, this should be covalent. I don't know why I wrote it as ionic. My bad. Okay, but anyway, we're comparing here. In all cases, these have non-metal elements, so they would all be classified as polar covalent bonds. None of these are truly ionic because there's no metals involved in any of these. Silicon's a metalloid, but that bond would still be classified as covalent. Okay, so let's go through all the different comparisons just one at a time. So if we have carbon-oxygen versus carbon-chlorine, so both of them have carbon in them, and it's helpful to remember some benchmarks. So carbon is here. It's going to be less electronegative than all the elements to the right of it, and it's also going to be less electronegative than most of the elements in the last column here. So carbon is less electronegative than both chlorine and oxygen. And again, it's not an obvious comparison, but between chlorine and oxygen, which is more electronegative? Oxygen is correct. So it's the second most electronegative element on the periodic table. So it is helpful to remember that. Fluorine is the most electronegative, then oxygen. So basically, if you're comparing oxygen to anything except fluorine, it's going to be more electronegative. So because it's a more electronegative atom, there's a bigger difference between carbon and oxygen. They're further apart in electronegativity scale. So we would expect carbon-oxygen to be more polar than carbon-chlorine, or have the larger ionic character. We're looking for the one that's the least polar. Now if we compare carbon-chlorine to carbon-fluorine, just so we can get rid of this one, we're looking for the least polar, so we can knock that one out. Now let's compare those two. And this one's a little bit even easier because, again, chlorine versus fluorine, as I just said, fluorine is the most electronegative atom on the periodic table. Both of them are more electronegative than carbon. So the difference between carbon and fluorine is bigger than the difference between carbon and chlorine. So CF bond is more polar or more ionic character than CCl. All right, so CF versus CCl. That one's going to be more polar, so this one we can knock out as well because we're looking for the least polar. And then the last one to compare, which is helpful because they share one element also, is carbon chlorine versus silicon chlorine. All right, so again, they both have chlorine in this case. Chlorine is the more electronegative atom in both cases, but we want to figure out which has the bigger difference. So from the periodic table, chlorine is over here, carbon and silicon is over here, so chlorine is clearly to the right and more electronegative than both of those. But be comparing carbon and silicon, which one is more electronegative? Carbon. Electronegativity increases as you go from bottom to the top. So carbon is more electronegative than silicon, which means the difference between carbon and chlorine is smaller than the difference between silicon and chlorine. And so what that leads to is, again, a more polar bond for silicon chlorine because, where did it go? Oh no, don't do this. Oh, come on. Okay, don't spaz out. Great. Let's see how much that recovers. If I have to write out those answers again, I'm going to... Not for you guys, it'll be my own frustration, but... Usually it usually auto-saves some of the annotations, but whenever it crashes, it'll lose some. Yes, restore it. Please restore everything, ideally. All right. Let's see how much it recovered. All right, we're doing okay. Where does it choke out? Oh, all the way back to number 6? No. Okay, we're good there. Good there. I guess I just didn't write much for number 6. Good there. All right, let's say we did okay. Okay, so we lost what we were doing here, but that's not too bad. Okay, save. So don't lose that again, although I didn't write anything yet. Okay, so what we said was, again, we compare them 2 at a time. So we had a smaller electronegativity difference for carbon and chlorine. So that one is more polar. We're looking for the least polar. Smaller electronegativity difference again for carbon chlorine than carbon fluorine. So that one's out. And then in comparing these last 2 here, we said that chlorine is more electronegative than both carbon and silicon, but there's a bigger difference between these 2 because silicon is less electronegative than carbon, and so that's going to be more polar because of the bigger difference. So again, this one with the smallest difference in electronegativity is carbon and chlorine, so that's going to be the answer choice that we would pick. All right, so you're looking for, if you're looking for least ionic character or least polar, then you look for the smallest difference in electronegativity. And again, I don't think it's a good idea to memorize the numbers, but having a few benchmarks in mind and sort of a few rankings that you kind of can just, rattle off really quickly are helpful for these types of comparisons. All right, any questions? All right, since the PDF crashed, let me make sure the video did not also crash, because it's all minimized here and I can't tell if it's even going. Looks like it's still going. All right, good. All right, we need to get going because we're lagging here. All right, and then number 15 deals with atomic or ionic radius. So it's, the atomic radius we kind of already covered earlier, but then for ionic radius we haven't really talked about it yet. Now the key concepts here for atomic versus ionic radius, if we're comparing a neutral atom to an anion, anions are much larger than neutral atoms. It's actually a huge difference. It's surprising. You can just add 1 electron to something and the radius just blows up. It's quite remarkable, actually, if you're... you guys probably don't think the same things are interesting as I do, but I think it's interesting. So anions are much larger than neutral atoms. So if we're comparing an atom to its own anion, then you set the anion to be much bigger. And then if you're comparing 2 different anions in the same row, if they're in the same row, look for the one that has the higher anionic charge, the more negative charge. So the one that has the higher charge, if it's -1 versus -2, you would expect the -2 to be bigger. you don't really have to worry about periodic trends when you're comparing anions as much because, again, the added electrons have a big effect. So anything that, and then if you're comparing two different rows, that's where, the row that is in the periodic table, if it's lower on the periodic table, closer to the bottom, that's going to be a bigger anion. So those are kind of the things we're going to think about. Which subshell are the electrons going into? And then, if it's comparing a neutral to if comparing two different anions, what's the charge? So for these ones, we have a couple of straightforward comparisons. We're looking for the largest radius. So if we compare oxygen to O2 minus, same element, but one of them has 2 extra electrons. Remember that anytime we add extra electrons, 1 or 2, however many, the atom gets much bigger. So we'd expect the radius of O2 minus to be bigger than oxygen. So we can get rid of oxygen because we're looking for the biggest one. Now, if we were to compare O2 minus to chlorine, that's a little bit of a difficult comparison because this one is in the 2p block, this one's in the 3p block. So there are two different subshells that have the electrons in them, but one's charged and one's not. So it's not an easy comparison. So I'm not going to bother with that one. Let's see if we can just get the answer otherwise. Now, if we compare then Cl minus to O2 minus, again, these are both anions. They are different charges in this case, but the more important factor is what subshells the electrons are in. If we're comparing two anions, even if the charges aren't quite the same. So as we said, oxygen is in the second row, so its electrons, even the 2 extra ones, go into the 2p subshell. So its outer electrons are in 2p. For chlorine is 1 row down, so its outer electrons are in 3p, including the extra one. And so again, 3p electrons on average are much further away from the nucleus than 2p. So if you're comparing two different anions that are in two different rows of the periodic table, the one that's in the third row versus the second row should be bigger than that one. So Cl minus is bigger than O2 minus, and of course, by the same argument, Cl minus is also bigger than chlorine because this is a neutral, this is an anion. So all the comparisons lead to Cl minus being the absolute largest of all 4 of these. All right, so for this comparison, again, two different anions from different rows of the periodic table. This has 3p electrons, this has 2p electrons. As you increase the n value, the electrons get farther away. All right, so that's how you would compare those. If you're comparing, cations and anions to each other, remember that in general, cations are smaller than anions, especially if you're talking about electrons that are all in the same subshell. So those are some things we talked about in class, so it's a little bit different than just comparing atomic radius. You have to consider the subshell that the electrons are in, the charge, and those kind of both factor in. Questions? All right, I will keep going then. All right, number 16 deals with predicting ionic formulas. So we want to predict the formula when calcium reacts with chlorine. All right, so this requires us, when we're predicting an ionic formula, we already talked a little bit earlier about how to predict the charges of cations and anions based on the location of the periodic table. So to get the ionic formula, we have to predict the charge of each ion, or if it's a polyatomic ion, we have to know what that charge is. So the phosphate, nitrate, chlorate, all those ones, you have to just remember what the charge is. There's no easy way to predict those. But once you know the charge of each ion, then you just have to make sure that you have the correct number of each ion to balance the charge, so that the positive and the negative charges completely cancel out. So here is calcium and chlorine, so those are the two elements. Ca and Cl are their symbols. So let's go then to the periodic table and predict what charge of ions we would have for these. So an ionic compound is always a metal with a nonmetal. The metal forms a cation, the nonmetal forms an anion, as we've already talked about. So calcium is here in group 2, so what do we expect the charge on calcium to be when it forms a stable ion? +2, right? Because it's in the second column, it's a metal. And then chlorine is here in group 7a, so what would its expected charge be? -1. It gains 1 electron to get to the argon configuration. All right, so those are the predictions we would make. Calcium is in group 2a, and all the group 2a metals form +2 cations. Chlorine is in group 7a, and all of those group 7a halogens form -1 anions. So that's the charge on each ion, so we just need to make sure they're balanced. And again, the sort of dummy way to do this without a lot of thought is just to take the charges and make them subscripts on the other elements. So the +2 on calcium becomes a subscript of 2 on the Cl. The -1 becomes a subscript of 1, and that leads us to the correct formula CaCl2. We need 2 -1 anions to balance the +2 charge from the cation. So they need to be the lowest whole number ratio, and they need to be 1 to 2 to make sure that the charge is balanced, so that would be choice A is the correct way to do that. All right, so questions on the formulas of ionic compounds. One of the more straightforward things we've done so far, just again, make sure you know your polyatomic ions, because those ones, the charges are not readily apparent from the name or the formula. Okay, so make sure you learn those, because they can come up as well. I think they come up in one of the problems later, but all right. Anything else? All right, the next one deals with Lewis structures. A deceptively simple one, but one that breaks some of the common sort of trends that we see for Lewis structures. So we have the Lewis structure for carbon monoxide. So this requires us to convert the name to a formula. So carbon, oxygen, both non-metal elements. This would be a covalent compound. There's no prefix on carbon, so that tells us there's one carbon. And then mono means one also, so that tells us there's one oxygen. So the correct formula is CO for carbon monoxide. So this requires us to take the name and convert it to a formula first to be able to draw the Lewis structure. Now we want to know what is the formal charge on the oxygen atom once we draw the Lewis structure. So now we're going to review Lewis structures and how to generate those. So we have 2 elements in this compound, and so we have to count the valence electrons first. All right, so carbon is group 4, so how many valence electrons does it have? 4. The group number also tells you the valence electrons. Oxygen is group 6, so how many valence electrons does it have? 6. Very good. So we can use the periodic table as well to predict valence electrons. So we have 1 carbon that has 4 valence electrons, 1 oxygen that has 6, and so we have a total of 10 for carbon monoxide. All right, so now we need to go through and try to draw a Lewis structure where the octet is complete on both atoms. These are both 2p elements, so you want to have exactly 8 electrons around each one. So we can start with a single bond. And then, as I said, the way that I like to draw Lewis structures is complete the octet of the outer atom first. Well, which one's the outer atom? There's only 2 of them, so that's kind of ambiguous. So it doesn't really matter which one you start with by convention, or makes a little bit more sense to start with the more electronegative one, but it doesn't really matter in this case. So we'll fill the octet of oxygen first. But then what we find is we've already used 8 electrons. We've done 2 from the bond, 4, 6, 8 to complete the octet. We only have 2 left. So we cannot also complete the octet of carbon. We don't have enough electrons to do that. So there's only going to be 1 lone pair on carbon. But we have a problem right now because at this stage, our carbon atom here only has 4 valence electrons around it. It has 2 from the bond, 2 from the lone pairs. That's only 4. And it wants to follow the octet rule whenever it makes covalent bonds. So it needs to have 8. So anybody have any suggestions on how we can remedy this? Yep. Yep, very good. So the suggestion was to draw a triple bond, and that's exactly right. Now we can't just add in 2 more bonds because that's going to add in too many electrons, but we take off 2 lone pairs from oxygen and convert them into triple bonds between the 2. So the correct Lewis structure for carbon monoxide would be this: carbon triple bond oxygen. It's not very common to have a triple bond to oxygen. It's also not very common to have a lone pair on carbon, but we have to do that here to satisfy the octet rule. There's no way to avoid that. So now the question is, what's the formal charge on oxygen? So if we calculate formal charge, we'll do it for each atom in the structure, although we only need to do it for oxygen in reality. So for the carbon here, remember that the way that we calculate formal charge is we start with the number of valence electrons from the atom, which is 4 as we counted earlier. We subtract from that the number of bonds that that atom has. Carbon has 3 bonds. 1, 2, 3 is a triple bond. And then we subtract from that the number of non-bonding electrons, which is 2. There's 1 lone pair, so 2 on carbon. So we get a -1 formal charge for carbon, and then for oxygen doing the same thing. Oxygen had 6 valence electrons. It also has 3 bonds, and it also has 2 non-bonding electrons, 1 lone pair. So the formal charge for oxygen is +1, and they should add up to be 0 because carbon monoxide is charge neutral, uncharged. So the correct answer for this is, what's the formal charge on oxygen? Would just be 1 or +1 would be the correct answer. So this is a weird structure because you have a positive formal charge on the more electronegative atom, but it's unavoidable in this case. It's the only way that you can complete the octet. So even though CO is a very simple formula, 1 carbon, 1 oxygen, the Lewis structure has a little bit of complications, but if we follow the octet rule and we follow the approach that I've outlined for drawing Lewis structures, we should get to this correct structure eventually. Okay, any questions on that?
What was the negative one?
The negative one is the formal charge on carbon. So if we'd ask you for the formal charge on carbon, it would be -1. So every atom in the structure is going to have a formal charge defined for it. Here we only asked for oxygen, but I did it for both just so you could see both, and also to make sure that they do add up to 0, which they should, because carbon monoxide is a neutral molecule. Yep.
On the test, would they depict different Lewis structures, and when we pick them, like, we won't have to physically.
Yeah, you can't draw on Blackboard very well. So yeah, so there could be questions where you select the Lewis structure that's correct, or there could be questions like this where you draw the Lewis structure on paper and then answer a question about it. But obviously you won't have to draw the Lewis structure into Blackboard. That's correct. Yep.
Do we need to know how to draw the Lewis structure for polyatomic?
So the question is, do we need to know how to draw the Lewis structure for the polyatomics? And yeah, that would be fair game. So you would start with the formula of the polyatomic ion, and then you would use the same approach. You would count the electrons, and then you would add in extra electrons if it's negatively charged, or subtract if it's positively charged, and then go through and follow the steps. So the steps are the same. It's still a covalent, unit. It just has an overall charge with it, but you don't have to do anything differently for that than you would here. All right. All right, 3 more. So here we're talking about names and formulas. All these are ionic compounds, as it turns out. We want to know which of the names and formulas is incorrect. Okay, so for these ones, we have to know some polyatomic ions to get them. I should have this problem somewhere. Not that I need to look at anything, but just trying to stay organized. Okay. All right, so in this one, we have to first make sure that the formula is correct based on the elements that are involved. So it's strontium 2 carbonate. So we're saying that strontium is +2. Carbonate is a polyatomic ion, which is CO3, and then you have to remember the charge for that is 2-. Again, there's no easy way to predict the charges of polyatomics, but carbonate is CO3 with a 2- charge. So this would be the correct formula, 1 of each to balance the +2 and -2 charge, but there actually is a problem with the name here. So I put here strontium 2 carbonate. Now remember, the Roman numerals in parentheses tell you what the charge in the metal is, but we only use those for transition metals or some of the metals in the P block. But if we find Sr strontium on the periodic table, Sr is here in group 2A. So for the metals that are in group 1 and group 2, we don't need to put a charge in the name of the formula, or in the name of the compound, because group 1 will always be +1, group 2 will always be +2. They're never variable, so it's redundant to indicate what that charge is. So that one is actually the one that's going to be the incorrect answer, because we don't use Roman numerals for main group metals. And more specifically for group 1A and 2A. So if the metal is from group 1A or 2A, you don't need a Roman numeral to indicate the charge. So that one is incorrect, so that would be our answer. Let's go through the rest of these, make sure they are in fact correct. So here we have cobalt 2 nitride. So cobalt is CO, and cobalt is here in the transition metal. So anytime you have a transition metal in your formula, you do need to put the charge in parentheses to indicate what it is, because the transition metals can have more than one possible charge. So if you don't indicate that in the name, you're not going to know what the formula of the compound is by looking at the name. So cobalt needs to have its charge indicated, so that one's fine. Then we have to make sure that the formula matches. So cobalt 2 nitride means we have a cobalt +2, and then nitride N. I'm sorry, I'm going to keep going back and forth, but nitrogen is here. So what's the expected anionic charge for nitrogen? Minus what? 3, good. So it's going to gain 3 electrons to get to neon. So that'd be the charge for that. And so the formula that you would get from cobalt 2 plus N3 minus, again, switch the names, switch the charges and make them subscripts, and you get CO3N2. That matches the formula. The name is good, so we're all good to go there. Calcium phosphate. So calcium is a group 2A element, so it's going to be 2+. We don't need the Roman numeral because it's in group 2A. And then phosphate here is PO4, and you have to remember the charge is 3-. So again, just swap the charges and make them subscripts. So the correct formula for calcium phosphate is Ca3, and the whole thing PO4 taken 2 times. So that's all correct there. Zinc sulfide, this is the one exception where you don't need a Roman numeral for transition metals. It's not really wrong to have it in this case, but it's not necessary either. So it's not obvious from the periodic table, but we do expect you to be familiar with it. So zinc is here. It's right at the end of the transition metal series. And zinc only forms +2 cations. The reason is that it has a 4s2 3d10 configuration, and it's fine losing its 4s electrons, but it wants to keep all 10 of its d electrons. It likes to have that filled d subshell. So this is one that you kind of just have to remember. I think there's a table in your book that sort of goes through those. So zinc will always be +2. That's one you more or less just have to remember. And then sulfur sulfide is also group 6, and so that's going to be S2-. So the correct formula for this would be 1 of each zinc sulfide. So that's correct. You could have the Roman numeral in parentheses, but again, it's not necessary here because zinc only forms +2 cations. It's never going to be anything else. And then finally, potassium chlorite. Potassium is in the column 1, so it's K+. Chlorite, we have all these different polyatomics with chlorine and oxygen, so let's go through those quickly. They all have a -1 charge, but they have different numbers of oxygens in the formula. So it's ClO, ClO2, ClO3, ClO4, all with 1- charge. We have to make sure we're straight on the names for those. So the ones that have fewer oxygens have the ITE ending, and the ones that have more oxygens have the ATE ending. The ones in the middle just have the root name, so chlorite and chlorate, for those two in the middle. And then if you have ClO-, you need a prefix hypo, which tells you it has even less oxygen, so hypochlorite. And then this one, I didn't give myself enough room, is going to be perchlorate. So there is a little bit of a pattern to it. You just have to remember that more oxygen atoms is 8, fewer oxygen atoms is ite, and then these ones also need prefixes to distinguish the two from each other in each series. So hypochlorite and then perchlorate for the one that has the most oxygens. So those are probably the hardest ones to remember because they're all so similar. But nonetheless, that's the correct formula, ClO2-, and if you have a +1 and a -1, you just need 1 of each. So KClO2 is the correct formula for that. Name and formula are both correct. All right, so it was the first one, A, that was incorrect because we don't need a Roman numeral if we're dealing with those first 2 columns of the periodic table. Any questions on nomenclature, especially ionic compounds? Yep.
So I was going to ask, what's the difference between using ite and ide? Like
Ite and ide. So IDE, ide, would be if it's just a single atom that acquires electrons to become an anion. So nitrogen 3-, or oxygen 2-, that would be nitride, oxide. If it's a polyatomic ion that has, most of them have an element with oxygen paired with it, so nitrate, phosphate, or phosphite, or sulfite, sulfate, the ending is going to be either ITE or ATE. The ones that have fewer oxygens in a given series are ITE. The ones that have more oxygens are ATE. So you don't want to change the endings on any of these anions. But if you're talking about a binary ionic compound where the anion is just a single element, then you have to add IDE to indicate that.
And for binary compounds, we only use that one time using the hypo or the hydro.
That would be true for acids that are binary. So I think there might be one question on acids here, but if not, the hydro prefix is only for binary acids, which would be, HCl, HF, HBr, etc., H2S, basically acid. So if a covalent compound that starts with H and has an anion after it. So those have the hydro prefix. That's the only time you'll see that. All right, anything else? All right, here's one that deals with some acids. So you'll see that here. All right, so here we want to know what the correct formula for the following covalent compounds. So we could ask you to type formulas into Blackboard. So it wouldn't be 3 formulas, so it'd just be 1 typically for a problem. But again, you just type the element symbol with a number and the element symbol with a number, no spaces. You don't have to try to subscript it or anything. Just type in the format that exactly is given to you. So dichlorine heptaoxide. So if we're dealing with these prefixes, then that should cue us in. This is a covalent compound. A binary covalent compound is the one that uses prefixes. And moreover, it's chlor, which is chlorine, ox, which is oxygen. Those are both nonmetals. So we don't even need to really look at the periodic table for this. We can just use the prefixes to directly translate them into the subscripts in the formula. So di means 2, so that means we have Cl2. Hept means 7, so that means we have O7. So for binary covalent compounds, name to formula is very easy because you don't have to remember charges because they're not ionic compounds. You don't have to look at the periodic table or make any predictions from that. It's just taking the prefixes and converting them into subscripts or going the other direction if we ask you to name the compound. So it's just, for binary compounds, very simple. The next two are acids, so it is a good time to bring up the naming rules for acids. So here we have hydrocyanic acid. This is actually the one acid that's not technically a binary acid because it has 3 atoms in it, but it still uses the hydro prefix. So hydrocyanic acid, cyanic is the ion cyanide, comes from the anion cyanide. So does anybody remember the formula for cyanide? It's one of your polyatomic anions. Cn, and what's the charge? I heard someone say it, I think. Minus. Okay, so it's Cn minus is the anion. And remember, whenever we make an acid, all we do is we take the anion and we just balance the charge with hydrogen. So if it's a -1 anion, it just needs 1 hydrogen to balance the charge. So the correct formula for this would be HCN. Now the reason it's given this name and not cyanide acid, I guess, the nomenclature that uses the IC endings, like we're going to see in the next one, that's only for what are called oxoacids, where the anion has oxygen in it. So cyanide is an anion that doesn't have oxygen in it, so that's why it follows still the binary nomenclature. But I think that's the only one that you'll see where the nomenclature looks like it's a binary acid with a hydro prefix, but in reality it's not binary because there's 3 elements and it has a simple polyatomic anion cyanide as part of the formula. But that's the only one where we'll have a polyatomic anion that uses hydro as a prefix. Okay, so that's one of the reasons I put it in here. So HCN, but again, name the formula. Even if you didn't remember that rule, you just have to find the anion that's associated with the acid and then balance it with hydrogen. And then same here for chloric acid. So if we see an acid that ends with IC in the first part of the name and does not have a hydro prefix, that means it comes from one of the polyatomic oxoanions, one of those anions that has a central atom with a bunch of oxygens around it. So to find the anion that's associated with it, IC goes with an ATE ending. What am I doing? Come on. I'm trying to draw a double arrow and I'm like losing it here. Double arrow, there we go. So an IC acid comes from an anion that has an ATE ending. Yes? So we're getting there, yep. So if you have a acid that ends in OUS, us, as you said, like chlorous acid, that would come from an anion that has an ITE ending. Okay. So that's the part of the name that's going to be key for identifying which anion is associated with the acid. So if it's chloric acid, that means the anion would be chlorate. There's no prefix in the name. The prefix would have to still be there if it was perchloric acid. Yep.
So are these prefixes in the book?
The prefixes should be in the book somewhere, yes, in the naming rules and all that stuff. And they're also in the notes from whatever day I covered nomenclature. But when you again, converting an anion, an oxoanion to an acid. If it's an ATE anion, it's an IC acid. If it's an ITE anion, it's an OUS acid. So this is an IC acid, so that means it comes from chlorate. As we just talked about in the previous example, chlorate is ClO3 minus. It's a 1 minus anion, so it just needs 1 hydrogen to balance the charge. So the correct formula for the acid that comes from that anion is HClO3. All right, so those are the correct answers for those 3. All right, so that covered a little bit about acid nomenclature, where you sometimes have the hydro prefix if it's a binary acid, or this one was cyanide. For all the oxoacids, you don't have a prefix, but the ending here tells you what anion it comes from. Any other questions on nomenclature? All right, we've gotten to the merciful end, so here we go. So this one comes back to Lewis structures again. In the Lewis structure of Cl2SeO that minimizes formal charges, how many double bonds are there and how many lone pairs are on the central selenium atom respectively. So here I told you that selenium Se is at the center, so that takes out some of the guesswork. And now we just need to draw a Lewis structure that minimizes formal charge. So the formula has chlorine, selenium, and oxygen, so we have to count the electrons. And I don't expect you all to know the periodic table off the top of your head, so if we go back to it, selenium is group 6, so is oxygen, so both of those would be 6 valence electrons. Chlorine is group 7, so it would have 7 valence electrons for each chlorine. So when we count those, we need those numbers to add up. So we have, 2 chlorines in the formula, so there's going to be 14 valence electrons from chlorine. We have 1 selenium in the formula, so there's going to be 6 valence electrons from selenium, and 1 oxygen, so there's also going to be 6 from that one. All right, so we need to draw a structure here that has a total of 26 valence electrons, and we need to minimize the formal charges as the problem asks us to do. So we put selenium at the center. We surround it with the 3 outer atoms in whatever order we desire. And the first thing we do is complete the octets on the outer atoms. All right, so we've done 3 octets, 3 atoms with complete octets now. 2 from the bonds, 6 from the lone pairs that are around each of them. That's 24 electrons. There's 26, which leaves us 1 for the central atom, 1 pair for the central atom. So this structure here would be the Lewis structure that follows the octet rule, because right now all 4 atoms in the formula have exactly 8 electrons around them. We completed the octets deliberately for the outer atoms, and our central atom now has 2, 4, 6 from the bonds, and 2 from the lone pair. So if we asked you to draw the Lewis structure that obeys the octet rule, we would stop here. But we're looking for the structure that minimizes formal charges, so we need to go through and figure out what those are. So if we look at the formal charges in this molecule for chlorine, selenium, and oxygen, chlorine had 7 valence electrons each. So we start with 7 valence electrons. Each chlorine has 1 bond. Each chlorine has 6 non-bonding electrons, so both chlorine atoms have 0 formal charge. And again, as we've noticed the pattern over and over again, when you have chlorine or fluorine or any halogen as an outer atom, they tend to form single bonds and have 3 lone pairs, and that's how they're going to be. But if we look at selenium and oxygen here, selenium and oxygen are both group 6, so they started with 6 valence electrons. The selenium in this has 3 bonds, right now, 3 single bonds, and it has 2 non-bonding electrons. So right now selenium has a +1 formal charge. 6 minus 3 minus 2 is 1. And then the oxygen right now has 1 single bond and 6 non-bonding electrons, which gives it a -1 formal charge. 6 minus 1 minus 6. So in the current Lewis structure, which does follow the octet rule, we have a +1 and a -1 formal charge next to each other. And if we're asking you to minimize formal charges, the way that we do that when you have a positive and negative next to each other is you draw an additional double bond. Now, as before, we can't just draw it in. We have to take off 2 electrons and change it to a double bond. So we're going to take off a pair of electrons from oxygen and convert it into a shared pair of electrons for the 2 selenium oxygen. So now with a double bond, these numbers all change. So oxygen, instead of having 1 bond and 6 non-bonding electrons, has 2 and 4, and that because it gets to a formal charge of 0. And then selenium now has a total of 4 bonds. And we didn't change the number of lone pairs on selenium. It still has the 1 lone pair, so still 2 non-bonding electrons, but that also comes out to 0. So this structure here, we had to expand the octet on selenium, which we can do because selenium's in the 4th row of the periodic table. We had to expand its octet, but we minimized formal charges, and that's what we're asking you to do here. So this being the correct structure now, we just want to know how many double bonds are there. So there's 1 double bond, and how many lone pairs on the central atom, also 1. So the correct answer would be B, 1 of each. 1 double bond, 1 central atom lone pair. All right, so the one that follows the octet rule would be 0 double bonds, but otherwise would be the same. Okay, any questions on this one or anything else before I wrap it up? Yep.
Are you going to reopen the homework?
The question is, am I going to reopen the homework? So the homework assignments are all opened up as practice homework. So if you go back into the homework folder, each homework assignment that already is due has a practice assignment associated with it. So you get 4 more attempts on that, ungraded. So however many times you want to do them or when you want to do them is up to you. But that's all available already for the ones that have already been completed. Any other questions? Okay, so good luck on the exam next week. I should be around for a lot of it. I gave my office hours in class on Thursday, so come find me if you have any other questions related to this exam.
I want to